What specific problem does your method address regarding the vocabulary size in LLMs? And why is this problem significant in the context of scaling performance?
Our method addresses the problem of determining the compute optimal vocabulary size for large language models, LLMs, which has been largely overlooked in existing scaling laws that typically focus on non-vocabulary parameters. This issue is significant because the vocabulary size directly impacts model performance. A larger vocabulary can enhance tokenization efficiency and representational capacity, but it also risks underfitting rare tokens, especially in data-constrained scenarios. We demonstrate that the optimal vocabulary size should be carefully balanced against the available computational budget and the number of non-vocabulary parameters, as our analysis reveals a power law relationship between these factors. By introducing a normalized loss formulation, we provide a framework to predict the optimal vocabulary size, which is crucial for maximizing performance while managing computational resources effectively. Ultimately, our findings highlight the necessity of considering vocabulary size in scaling LLMs to ensure they can effectively capture the complexities of language.
How does the proposed method or algorithm work? Illustrate the methodology step by step, particularly focusing on the 3 approaches you introduced for estimating the optimal vocabulary size.
The proposed methodology for estimating the optimal vocabulary size consists of 3 distinct approaches, each designed to analyze the relationship between vocabulary size and model performance under varying computational budgets. 1. Approach 1. Estimating power laws via isoflops involves pre-training models with non-vocabulary parameters ranging from 33M to 1. 13b, while keeping the flops constant across different vocabulary configurations. By fitting power laws that relate flops to both non-vocabulary and vocabulary parameters, this approach reveals that optimal vocabulary parameters grow at a slower rate than non-vocabulary parameters, indicating a power law relationship. 2. Approach 2. Derivative-based estimation utilizes the derivative of flops concerning vocabulary size to find the optimal vocabulary size that minimizes loss. This method computes the minimum point of flops with respect to vocabulary size, allowing for a numerical search to identify the optimal vocabulary under a given loss target. 3. Approach 3. Parametric fit of loss formula modifies existing scaling laws to incorporate vocabulary size and fits a loss function based on non-vocabulary parameters, vocabulary parameters, and training data. This approach allows for predicting the optimal vocabulary size by finding the minimum loss concerning vocabulary size, even when the allocation of parameters is suboptimal. Together, these approaches provide a comprehensive framework for determining the optimal vocabulary size in large language models, emphasizing the importance of balancing vocabulary and non-vocabulary parameters for effective scaling.
What are the theoretical or practical benefits of utilizing your proposed normalization of loss function with respect to vocabulary size?
The proposed normalization of the loss function with respect to vocabulary size offers several theoretical and practical benefits. Theoretically, it allows for a fair comparison of model performance across different vocabulary sizes, as the traditional language modeling loss is inherently biased towards larger vocabularies, which naturally yield higher loss values. By employing the unigram normalized language model loss, we can assess the model's efficacy without the confounding influence of vocabulary size, ensuring that the differences in loss reflect the model's true performance capabilities. Practically, this normalization enables researchers and practitioners to identify the optimal vocabulary size more accurately, as it highlights the model's ability to improve probability predictions over a baseline unigram model. This leads to better informed decisions regarding vocabulary allocation, ultimately enhancing the performance of large language models in various applications.
How did you validate the effectiveness of your proposed method? Describe the experimental design, datasets used, and the benchmarking metrics you employed.
To validate the effectiveness of our proposed method for determining the optimal vocabulary size, we conducted experiments using models with 3 billion parameters, specifically focusing on the compute optimal training flops budget. We compared a baseline model that utilized a common vocabulary size of 32K against another model that employed the optimal vocabulary size predicted by our approach 3. The datasets used for training were uniformly sampled from different domains within the Slim Pajama dataset, ensuring a diverse representation of text. We evaluated the model's performance using the normalized loss function, L_U, on a held-out validation dataset, which allowed us to assess the efficacy of the language models while accounting for varying vocabulary sizes. The results demonstrated that the model configured according to our vocabulary predictions consistently outperformed the baseline across multiple downstream tasks, thereby empirically verifying our predictions.
What specific results did your experiments yield, especially in terms of how the optimized vocabulary sizes impacted the performance of language models?
Our experiments demonstrated that models utilizing the optimized vocabulary sizes predicted by our approaches consistently outperformed baseline models that employed commonly used vocabulary configurations, particularly when both were evaluated under the same flops budget. Specifically, we trained models with 3 billion parameters and found that those allocated according to our vocabulary predictions yielded better performance across multiple downstream tasks, as shown in Table 10. Additionally, we observed that the optimal vocabulary size increased when training on excessive amounts of data, indicating a mechanism to prevent overfitting, while it decreased in data-constrained scenarios to avoid underfitting. This empirical evidence underscores the critical role of vocabulary size in enhancing model performance, particularly in relation to the amount of training data available. Overall, our findings highlight the necessity of considering vocabulary size as a key factor in the effective scaling of language models.
What limitations did you encounter with your proposed approaches, and how might they affect the generalizability of your findings?
The proposed approaches in the paper, while effective in estimating optimal vocabulary sizes, face limitations that could impact their generalizability. Firstly, the approaches primarily rely on empirical data from models with specific configurations, which may not universally apply to all LLM architectures or training regimes, particularly those with significantly different parameter distributions or training data characteristics. Secondly, the assumption of optimal data allocation, as seen in the scaling laws, may not hold in real-world scenarios where data scarcity or excess can skew results, leading to potential overfitting or underfitting issues. Additionally, the methods do not account for the computational overhead introduced by larger vocabularies during inference, which could affect practical deployment. Lastly, while the approaches suggest a power law relationship for scaling vocabulary parameters, this relationship may vary across different model sizes and architectures, limiting the applicability of the findings to a broader range of LLMs.